it would be very naive to think that if you are upgrading only your ciphers and you are keeping pseudo randomness as the input of your cryptographic value chain, that the attacker will be very gentle to only use one algorithm to attack your system.
Rip and replace is unfortunately going to be a part of PQC migration. But one company is trying to save at least some servers from becoming e-waste with a plug-and-play solution. EigenQ accelerator boards combine quantum entropy with NIST PQC algorithms. Find out how practical quantum hardware is solving real-world security challenges today in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of EigenQ, Dr. José Rosas. Welcome to the show.
Thank you for having me, Konstantinos.
Yeah, before we dive in, I guess if you just want to spend a moment to let listeners know a little bit about your company.
Yeah, so we are an applied quantum technologies company. We specialize in photonics. And nowadays, we're trying to take an aim of different kind of problems, being cybersecurity and performance, the first one that we're tackling using quantum technologies itself.
Yeah, and it's one of those use cases that kind of caught my eye. I know you guys have some new accelerator boards that came out.
Yes.
And maybe you could talk about those. I guess the promise is to make old technology servers PQC ready without just throwing the servers out, right?
Yes, and it's an interesting challenge. We have around $30 trillion worldwide in infrastructure that actually at some point they will have to be renewed. But while we are waiting for these new versions, we have to do some sort of retrofit. And it's a huge challenge because it's technology that was not being designed to manage these workloads. And they have different form factors, and they're usually long-lived devices, and they are part of our critical backbone on our economy. So it's something that we need to take care of it. So as part of that, we have been designing different form factors that goes into different part of this infrastructure in an attempt to retrofit them as soon as possible.
So you take, let's say, a legacy Xeon server or an EPYC server, and you install a board, and then that board offloads the cryptographic workload?
Yeah. So what happens in the market is that the quantum threat is being a moving target, and people were developing solutions that they thought that being ready by 2040 will have been enough in the market. So it's all these brands that kind of like, they have the resources, the incentive to create the solutions, but in allocate resources take a long time. So everyone was ready by 2035 to put something in the market that is native to their platforms. And then all of the sudden, then we were start hearing about 2033, 2030, 2029, and 2027. So now you have this gap in the market that we know that down the road we're going to be okay. But the challenge was what we can do in the interim without modifying actually the motherboard or the platform itself. So in a particular case, we come up with a solution that are very similar to other platforms, but a particular solution that we came up for the Xeon platform is there any port that we can use that will be easy to plug something that actually will present the solution to the operating system and the platform and will make that platform compliant without replacing the motherboard itself. So that's kind of like, the engineering challenge that we have. And we created a couple of form factors that nowadays are integrated in standard PCIe boards that where you're able to mix quantum technology itself with conventional cryptography and post-quantum cryptography. And those boards actually act as an anchor for the full stack because there is software and library solutions as well, but it provides a full stack upgrade to those kind of platforms.
So you're using like PCI boards or something to
yeah.
basically...
So basically the solution actually when you look like, and that is the reason because partners like HPE and others have been selecting us, is because The solution is practically a plug and play solution. So
Mm-hmm.
they follow their own manufacturer. When you're building a server, you usually work with different providers like memory RAM providers, hardware providers, and the like. They usually go into a manufacturer facility when they assemble all of these devices together into what is going to be a server. And we just piggyback in that value chain. And then we were saying, listen, this is just another component that you will have to integrate as part of your process, no changes on your motherboard. And you will plug this, upgrade the firmware, and it's just going to work. And that was our value proposition, kind of like, almost 2 years ago. And they were like, that sounds complicated. We believe that you will not be able to pass the internal security of the platform, or they were saying kind of like, the stuff is going to be very difficult to make it compatible. So it was not a well received idea at the beginning. But after a while, it's just become the logical thing to do. And after a year and a half, we were able to actually launch the first versions commercially, this on June 17 in Vegas. The first server that had these quantum resistant capabilities already integrated by the manufacturer itself.
Yeah, I mean, they're high throughput slots because that's where you're supposed to put like a RAID controller or something like that, right? To get those servers to handle a lot of throughput. So what kind of engineering bottlenecks were there? I mean, so we have, do you have some kind of, what kind of like processor and everything is handling the math for MLChem, MLDSA? Like basically that's like a combo question, I guess.
So what happens is like at the end, what you realize that these kind of solutions are, the need for a hardware comes from different reasons. And of course, in a platform, you have a processor that is already dedicated for, conventional workloads.
Mm-hmm.
But that workloads actually are accessible for the whole operative system. If your operative system gets compromised, chances are that the cryptographic that belongs in that server will be compromised as well. So in addition to that, the engineering challenge was how we can get a quantum phenomena integrated in conventional silicon. So you have a normal PCB board, and we wanted to have a quantum mechanic phenomena that could live in that PCB board as the anchor of security for the whole value chain. So, and we're discussing here quantum entropy. We're discussing that the only thing that a quantum adversarial will not be able to predict with a deterministic approach, it would be if you have a quantum entropy phenomena. So the challenge is that how you put a quantum entropy phenomena in a conventional PCB board that is connected to a PCIe card. So that is the first challenge. The second challenge is how do you use that to leverage and enhance all the cryptography that you have down the road, MLChem or kind of like, the other PQC ciphers, how you connect those two to create a unique solution. And this is what we offer, that is a quantum entropy mixed with post-quantum cryptography ciphers in a trustless solution that is a plug-and-play solution. So then in order to achieve that, then you have many, many challenges to overcome, yes.
So you're not providing just the ability to run lattice-based math faster, you're also providing random number generation.
Yes, quantum random generation based on quantum entropy. And so the conjunction of those two is actually what creates the most probable secure quantum resistant approach. It will be very naive to think that if you are upgrading only your ciphers and you are keeping pseudo randomness as the input of your cryptographic value chain, that the attacker will be very gentle to only use one algorithm to attack your system. So there is a lot of people that are only concerned about attacks made by source algorithm. And this is basically increase the factorization or decrease the factorization time of prime numbers. But in a quantum computer, you can use Gruber algorithm that basically is able to diminish the time by half of sorting any random set of data. So the attacker will use conventional attacks, it will use conventional devices, it will use multiple quantum algorithms in the quantum devices, and it will perform an attack that is at different parts of the value chain of the cryptography, not only on the cipher, but at the beginning, the industry was only focused on let's upgrade the cipher. but that is the same thing as putting 1, 2, 3, 4 in as your password. It doesn't matter what is the encryption that you're using to store your password. If your password is 1, 2, 3, 4, it's still a weak solution.
Yeah. To detangle a little bit for listeners, right? So with Grover's algorithm, that's a attack against a key search, basically.
Correct. Yes.
So and it doesn't really have the time. What it does is it has the number that's the exponent. So for example, if it's 2 to the 128th searches, it's 2 to the 64 searches. That's not really half, but it's in terms of time, it just makes it like smaller. So so you're concerned here with not only replacing the old ciphers like factoring numbers, difficulty 2 lattice based for those applications, but you're also adding the ability to use random number generation and other kinds of application layer
in conjunction. It has to be in conjunction. Yeah. So
is there like an SDK? Is there something to fully enable the board? Because otherwise it might just sit there and do one thing.
Yeah. So also like the same board also comes part of the value chain of the root of trust and the secure boot as well. So when you're booting the server, usually the base platform will have certain level of security, like a secure boot. Then we have signatures that goes into the board, and then the board itself also allows to have a virtual quantum resistant TPM that becomes part of the secure boot, and also allows you, before presenting to the operating system, to have quantum resistant public key infrastructure signatures that will sign the device before the device even starts and is presented into the operating system.
I was going to ask you about that, because without TPM2, you're open to all sorts of attacks. So you're injecting into that boot part of the boot loading.
Correct. And then after that, you present to the operating system a fully integrated platform that is replacing the default randomness with quantum randomness. And in addition to that, you have libraries that provide the post-quantum cryptography ciphers to the operating system. And then in certain solutions, we go up and even we provide an application layer. For example, a VPN client that is already using the stack that is below, or we provide the libraries, the SDKs, and the use of the replacement of the virtualized quantum random number or the conventional quantum random numbers. So then, for example, hypervisors or web servers and other applications can feed from these new resources that are presented at the operating system level.
Oh, wow. Okay. So there definitely is software that will have to run on the machine for the user level, user land, right?
Correct. It's the firmware, and then in the application layer, there are libraries, SDKs, and the like. And there is also API services, because one of these servers, for example, can feed a cluster of servers. So sometimes you cannot upgrade all the servers and put a card in each of them. Sometimes you will be able to add a new server to that cluster, and then the others can feed through a secure channel through an API in a local network. So it's different kind of architectures that we do for deployment.
Interesting. So you'll be able to protect applications running on other servers that way. But you wouldn't be able to do the integrated boot process.
Correct. And it's of course, it's depend of the level of paranoia.
Yeah,
for example,
exactly.
Sometimes you have, for example, air gap solutions that actually they have a gateway. So basically, it's good enough to have the gateways or the in and out of that secure environment to be protected, because you're actually sure that there is no other way that there is physical access to those devices. But then you have other scenarios when we have other form factors, when you have devices deployed in tactical environments like drones or UAV and the like, that for sure they are going to be intervened. So then in that scenario, you want to have kind of like, root of trust, secure boot and the like, that is quantum resistant, not the conventional.
Yeah. This is really interesting, because it sounds at a glance like you're just dealing with offloading some of the cryptographic processes, but you're really adding new layers of functionality to the machines that never were there.
Totally. And also, like, we go even up, for example, the endorsement and the relationship that we're having now with certain partners and the collaboration we have with AMD and Intel allow us to run our workloads in the trusted execution environments of the CPUs. So it's not even that we run a piece on the boards, but then also we run part of the workloads of the value chain of the cryptography in the secure areas of the CPU that is available in the hosting machine. And we can do that for very small devices, and we can do it also for data centers, CPUs as well. So then you have a solution that is protecting from the workloads that runs in the CPU all the way down to the secure boot integrated in that value chain. So that creates a full stack optionality depending on the application.
So I would imagine there's an extra level of upgrade needed, right? Going forward, you're going to have like firmware updates for your board then that need to be applied.
So kind of like, going forward, what we have seen in the market is that the vast majority of the next generation solutions are going to be SoC based, basically silicon based. A system on chip will have these properties, and then in that world you have a trade-off that is cost and basically performance versus the problem that the ciphers are going to change over time, and whatever you are putting in your silicon today might not meet the long life devices certification that actually you may need for this kind of solution. So what happens with post-quantum cryptography and quantum resistant tech, this is the ultimate crypto agility challenge. There is no algorithm that will be proven for the next 20 years, like future proof. And many things will change, the size of the keys, the algorithms itself. So I believe that the industry is moving too quickly into silicon, and that could be a mistake, but this is what we are seeing there. The approach that we are taking is an approach that is more in the middle ground, so an approach that actually allows us to upgrade the ciphers. So actually in our roadmap, even the board is a physical board. We create it in a way that we can upgrade the firmware and certain components of the board over the air, with the understanding that the parameters of the ciphers may change, that the ciphers may change itself down the road. So as I was saying before, like this is the term is called dynamic hardware reconfiguration, and this is kind of like it's a new paradigm in terms of hardware itself. Is an old paradigm that actually is taking a new breath because of this challenge, but there is no other way around if you want to do crypto agility.
So you're not tied to lattice-based math. If for some reason we went to multivariate or code-based or whatever, you guys could just adapt.
Correct. Of course, the challenges are gonna be like at some point the hardware has limited resources, and then like if we are increasing the size of the keys and is 1,000 times bigger, of course there is certain things that you will not be able to do. But by the same token, is, as I was saying before, even today we already started a new NIST batch with potential new ciphers. So we're not even implemented the lattice-based ones, and we already have entering a new phase when we may select others. And then you have, for example, other parts of the world like China that is creating a totally different approach about quantum resistant ciphers and technology.
Yeah, ISO standardization of classic Michaelis, for example.
Totally. So then kind of like, as a company, if you have a global reach, kind of like, the understanding of having a very specific silicon, a silicon-based solution, it will take like between 2 to 2.5 years to develop and to stabilize the silicon. And then you have the reduction of the form factors, and then you have the integration in the platform itself. So it's a 3 to 5 years process. And it's very likely that in that time frame, you may have another cipher out there.
Yeah, and now we have the accelerated timelines because of executive orders and everything.
Yeah.
And people need to migrate. It's literally written in the order that we need to migrate, and we might have another one to consider before the migration even completes.
Correct. So then we have kind of like, these discussions that we have among like the security experts, because there is always this conflict about compliance versus actual security. So on one token, like you have the mandates and then you need to be compliant, but because you need to be compliant, you may be choosing a solution that actually is less secure. So compliance and security are not things that actually go in tandem. That could be actually hitting each other in certain cases. So in as a company, our decisions actually has to be made and in taking into consideration these two worlds, that you need to have a world where you need to allow compliance, but at some point our solution was seen by experts to be over the top and kind of like, too secure for what the use case was at the time. As the market moved on, they were like, oh, this makes sense. Then kind of like, oh, and this is kind of like, the proper way to do it. So we're very lucky to be a little bit paranoid in that sense, and that the market move in that direction.
Yeah, and then things can change for reasons that have nothing to do with security. Like the CMMC
Totally.
in the U.S. security, it was suspended a couple of weeks ago as we record this because of budget issues. Like basically,
yes, totally.
Yeah, so who knows what's going to happen because of that?
Who knows what's going to happen? So and it's like, and at the same time, kind of like, you have the fundamentals of security. Kind of like, there are solutions that are better than others, that there is no question about that. There's an understanding on the community about that. But then when you hit the commercial piece, you hit things like cost, and you hit things like, well, why we will do this if there is no requirement? So, and then why we will do this if there is no need to compliance? So then you have these drivers that actually kind of like, are pulling a solution into different direction, and then you need to find kind of like, sort of a middle ground that create a product that is commercially viable. This is a challenge in many industries. Telecommunications now, for example, they have a huge challenge with the eSIM provisioning. The eSIM provisioning is a process that is not quantum resistant, that requires a whole ecosystem to change. And where are the incentives to do it?
Yeah, it's not like there aren't a lot of mobile devices, right? Come on, I mean that's really, really bad. The eSIM.
No, but there you have it. It's like kind of like, yeah. So, but there, of course, at some point it's gonna hit a compliance issue. And when they hit a compliance issue because of a regulation, then you're going to have an incentive. But from the security perspective, the eSIM technology is the most popular technology that is growing, that is creating the most accelerated footprint, and is the one that actually is vulnerable to quantum attacks in the provisioning of the electronic SIM. So that from the security perspective, that will be the first one that I will, as humanity, I will say, well, that is the first problem that we need to solve.
So I was going to ask if there were certain areas that have a steep compliance curve to face, and you just offered this one. Are you planning some kind of solution to help that problem?
Yeah, so we got invited to join the GSMA, and we're in the process to see if we are going to qualify for their acceptance. The GSMA is the group that congregate the vast majority of the telecommunication companies of the world. And we had developed some solutions. There is many groups that are actually been working on solutions to this particular problem. So I will say it's not the lack of solutions, it's the lack of incentives. So in that case, telecommunications are a very regulated industry. So you have the standards, but the standards usually are driven by the community. The community is creating the standards. Nevertheless, if a government says, listen, you need to fix this stuff, that is going to accelerate a timeline. Otherwise, it could be sitting there 20 years in a highly regulated environment that will take a lot of effort without commercially driven incentives.
Do you guys play at all on the other side of this whole problem, the helping identify your existing vulnerabilities? Like right now, we know, like with example, Executive Order 14412 by September, high value assets, those have to be taken care of with CBOM, cryptographic bill of materials, all that good stuff. Do you have any kind of way to provide insight on that?
So we have, actually, it's funny enough that we have partners that approach to us to do two things. So one thing is that they are offering to discover quantum vulnerabilities, but they are not themselves quantum resistant. So that is kind of like, one of the kind of like approaches that we have on companies that are coming to us and creating that. The other one is we have a quantum resistant public key infrastructure that actually becomes very handy for the CBOM and the other parts of the discovery and certification itself. So those other collaborations that we're having as well with companies that provide those services. We as a company, we are not into that business, but we collaborate very tightly with the ones that actually are doing that, because they become, at the end, they become a part of our pipeline. They are discovering potential customers for us. So it's a very synergetic relationship that we have with them.
And don't be too hard on partners that aren't post-quantum ready, because even with the executive order, as aggressive as it is, it even says that to be a contractor, you don't have to be PQ ready until.
Yeah, correct. But
So
what I was
too.
saying is like they're not driven by compliance. They're driven by their marketing efforts. It says, well, I'm selling this service, so at least I want to claim kind of like, that I have certain quantum resistant capabilities.
Yeah, that's true. Eat your own dog food, or whatever the expression is. So I want to ask, you guys have a huge $3 billion SPAC merger.
Yeah.
Right. So how is this influx of market capital shifting your scaling strategy?
Yeah. So we entered and announced a DSPAC transaction. Actually, it was in June 17 in Vegas, concurrent with this launching this product along with the HPE. So it was a busy week. Yeah, so of course, everything is subject to SEC review and the like, and there is many things that could go wrong in these kind of transactions. But we're targeting to try to complete the transaction by the end of the year, and I will say, in terms of and how this story fits with other stories, is that being a quantum company that is chasing the compute infrastructure itself is kind of like a very unique story. Like in our roadmap, we have quantum artificial intelligence, quantum communication, and a quantum platform itself. But we make this conscious decision to create building blocks and put products in the market that actually allow us to capture revenue, and then use that as a building block for the next phases. The market recognized a lot of value on that story. I think it's been appreciated as a different way to do it, compared to, there is kind of like more than 11 companies that are public already that play different parts of the role in the quantum ecosystem, and each of them are being successful because they make a conscious choice on a particular problem in the market. And I think we took a page from that book, and we make our choice to specialize in this particular problem, and fortunately the market is moving in that direction.
So I was thinking about your general approach before this interview, and if you're doing plug-in boards to help remediate older hardware, eventually that older hardware will end of life anyway. I mean, people are going to just stop using it eventually. So I assume then your plan is to transition to other types of technologies and plug-ins, and maybe does any of that center around like this idea of the quantum internet, for example? Like, do you envision adding boards that help communications or security protocols there?
So in our case, the way that we see it is that we love the compute infrastructure vertical. The compute infrastructure vertical globally is around 462 billion in revenue per year. So any penetration percentage that you can do in that particular vertical actually are very, very attractive numbers.
Yeah, of course.
and then you have like this retrofit opportunity. It has a window that might last 3 years. And it may have a tail, but let's say we can assume that it's 3 years. The actors that play a relevant role in this vertical, I think that around 10 of them, and those are the ones that actually are incumbents, and they are trying to get an edge against what could be a potential future quantum compute infrastructure. So then you have all these other companies that may or may not working with these actors that are developing something that may or may not disrupt the compute infrastructure itself down the road. So in our case, we decide to partner up with the incumbents and provide them solutions that will give them an edge against the potential quantum threat in the business side to their dominance position. So in that sense, the first product are effectively quantum cybersecurity and compliance that we call. The second vertical that we have is quantum artificial intelligence and performance. So it's a series of products that we expect to put in the market by the end of 2027 that are designed using photonics and other quantum technologies to optimize different parts of the workloads of the compute infrastructure. The beauty of it is that it's the same actors. We already established a relationship. We already have the endorsement. We already help them, to have an edge in the cybersecurity and compliance. We know that the next big problem that they have is artificial intelligence workloads and performance in general. So our next generation products is still working with them and to help them to have a quantum edge by using our devices and integrating our devices in their platform.
So I'm assuming you can't give too much away right now, but I think it sounds like, correct me if I'm wrong, it sounds like you're trying to do the whole quantum for AI thing without throwing an actual quantum computer at it. Like you're going to pick pieces of it that a device can, just like with QKD, you don't use a quantum computer, you use diodes or whatever. Yeah.
So exactly, I think you got it right. And the ones that we can discuss, not specifically on the roadmap, but we can discuss in general that you can get the example of analog devices. So analog devices in the past, you will be able to solve fluid dynamic problems or differential equations by tuning certain physical phenomena that by just tuning some knobs will give you a solution of a very complex mathematical problem. So when you have these, not the universal quantum device, but when you have a purpose-based device, you can apply the same logic. There is certain problems that actually the quantum devices may solve way, way more efficiently than conventional ones. In our overall architecture, though, is not a rip and replace again. Kind of like, we're not against the conventional silicons. We are very utilitarian in that sense. We take the same approach that we're taking now for this next generation. We're using as much as we can the existing resources, and we're just trying to complement that with these specific devices that will help in that particular problem.
No, that's great. I love the idea of zeroing in like that. It's such a common misunderstanding in the world that whenever quantum numbers are reported and benchmarks are reported, like the famous Willow operation, everyone thinks that applies universally in some way, like random circuit sampling. It's like, whoa, a quantum computer was better at random circuit sampling than a classical computer. Well, yeah, of course, because it's just simulating what it is, really,
Yeah.
So it's like, it is smart to target what it's actually capable of doing.
Correct. And it's like, as one of the things that is interesting, that if you think about it a little bit, the quantum device itself, they were envisioned like hundreds of years ago, almost at the same time when the von Neumann architecture actually was envisioned. The reason because we ended up with the silicon is that we were able to build the transistor and the silicon that actually will enable us to deploy a von Neumann architecture. But then down the road, it took us a long time to actually find a way to implement quantum phenomena itself. But those ideas are not new. They're very mature ideas.
Yeah, I mean, quantum mechanics was formalized over 100 years ago now. So.
Yes,
it's not exactly a new concept.
Correct. Yeah. So it's an interesting time that we are living because, we are able to build things that actually can complement conventional von Neumann architectures with quantum devices, and in the process you can create these amazing advantages. It's a very unique situation that we are.
Everyone's interested in that space for sure. Everyone wants to know, can a quantum computer be paired up somehow to help along the workloads of AI. And I would be very interested to see what you guys come up with next. So thanks for giving me that tiny little sneak peek.
Next year, you're gonna hear from us a little bit, maybe earlier. I think we're planning to make some announcements maybe like by mid next year. But yes, it's a problem that we're working on. It a very interesting problem. It's like and also like going into is the expansion on this goes into networking, and then finally in something that we call that is distributed quantum platform. So we don't believe in a single quantum computer. We believe that you are going to have many devices deployed in different parts of the ecosystem. And then the next challenge is to interconnect those devices. And after you have that, you have a distributed quantum workload network that acts as a platform. So, and this is all complementary because you still have kind of like photonics is the most advanced communications of the world. The delta between photonics and quantum photonics is a problem that we are addressing. And it's a very interesting problem because we have so much infrastructure that is already being deployed. Mm-hmm. And then you have the problem of processing as well. But all of that goes into a natural progression where we did this in the past. You have amazing devices. The next thing you want, you interconnect them. And then after you interconnect them, you want them to work together. This is just a logical process that we're following in our roadmap.
Yeah, interconnect is critical. And anything that could be done over telecommunications networks that exist, of course, it's a no-brainer.
Yeah, so it's like, and then now you have all the, the workloads coming into space as well, kind of like, and then guess again, what is you use to communicate that? Well, you use photonics again. You have radio frequency and photonics, and then you are having more workloads going into space. So at the end, I think if you take into consideration the amount of capital that is invested in infrastructure, and you find a way to use those rails to deploy your solution, I think you are onto something.
Great. So I guess I'll be having you back on in 2027 with at least something that improves the whole quantum for AI situation. So
yes,
the challenge is out there, so you have to accept it. Thanks so much for coming on, Dr. Jose.
Thank you very much, and thank you for having us.
That does it for this episode. Thanks to Dr. Jose Rosas for joining us to discuss EigenQ. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.